Hello everyone, my name is Jianliang. I'm a PhD student from Purdue University. Today I'm going to present LIGHTBLUE, an automatic profile debloating framework for Bluetooth stacks. This is a joint work with EPFL and CISPA. So Bluetooth devices are everywhere. According to Bluetooth Special Interest Group, there will be over 5 billion Bluetooth devices all over the world. And Bluetooth can be used in different cases, such as audio streaming, printing, smart home, and healthcare. Supporting the different use cases means that the stack is bloated. First of all, there are multiple profiles in Bluetooth stack, such as JTT and PAN profile. To support the different profiles, there are different protocols, like L2CAP and ATT. Besides from the host code that I just mentioned, there is also firmware running in the Bluetooth controller. Assume we have a point-of-sale app that only uses the GATT profile and related protocol. Then the other profiles and protocol are not needed. However, they might be vulnerable. Here is a real example in the real world. The Square app only uses the GATT profile and related protocols to communicate with the Square credit card reader to read the information of the credit card. Therefore, the other profiles and protocols can be removed without affecting its functionality. So our goal is to debloat the unneeded code in the Bluetooth stack, so the vulnerabilities within the Bluetooth stack are no longer exploitable. Besides, the framework should be automatic to remove unneeded code, and it should be flexible to debloat different profiles. And at last, it should support full stack debloating. It could debloat both the host code and the firmware. So the first step of the framework is identify the needed profile by an app. Once the needed profile is identified, it then performs the host code debloating and firmware debloating. Recall that those two pieces of code are running on two different CPUs. Therefore, we analyze them separately and use the HCI commands to bridge the gap between them. The first step is kind of straightforward. The app calls the APIs provided by the system to use a profiles functionality. Therefore, we scan the APIs in the app to determine which profile is needed by an app. Once the profile is identified, we perform the host code debloating. So the first step is to determine which part of the code is needed by the profile. One challenge is that different profiles might be coupled. For example, in this function, the functions from different profiles like hands-free, headset, and A2DP are coupled together. So one solution to this problem is the per profile data analysis. The function at the right side is from the A2DP profile. If we can make sure that only the A2DP profile is needed, and we could propagate the constant value in the right function to the functions at the left side, then we are able to remove other switch cases in the left function to decouple different profiles. However, one profile has several entry functions, like the code snippet shows, which makes the data analysis cannot directly apply. To solve this problem, we transform the multi-entry interface into a single entry interface. Specifically, we divide the profile entry functions into 3 categories: initiating, functioning, and ending. And then we create a dummy function calling the entry functions in such an order to mimic the profile life cycle. The dummy function calls the initiating functions first, and then the functioning functions, and at last the ending functions. After this, we perform the data analysis to decouple different profiles and identify the needed code of a profile. And then we are able to remove the unneeded code and extract the used HCI commands from the needed code. The extracted HCI commands will be used in the firmware debloating. When the firmware receives an HCI command from the host code, it first dispatches this HCI command to its corresponding HCI command handler, and then the handler handles this command. So the most important step is to identify the dispatcher function. The closed source nature of the firmware introduces unique challenges to the identification. So LIGHTBLUE uses a two-step approach to identify the dispatcher function. First, it scans the whole firmware to find all the candidate functions, and then it verifies each of the candidate functions to find the correct dispatcher function. This figure shows the format of an HCI command. As we can see, it contains an opcode field consisting of OCF and OGF two subfields. So in order to correctly pass an HCI command, some bitwise operations are needed to extract the OCF and OGF value. Therefore, we scan for functions containing those bitwise operation patterns and find all the candidate functions. Then we verify each of them using the HCI command semantics. This picture shows the read Bluetooth address HCI command. So we set the opcode to the read Bluetooth address command and symbolically execute each of the candidate functions. Then during the execution, we check whether the expected value is accessed or not. Here, the expected value is the Bluetooth address. If the expected value is accessed, we can make sure the current candidate is the correct dispatch function. Once the dispatch function is identified, we can easily identify all the HCI command handlers. Recall that we extract the used HCI commands from the host code analysis. So here, we could keep the HCI handlers that handle the used HCI commands and remove all other HCI command handlers to debloat the firmware. We implement LIGHTBLUE based on LVM and Anger. And we evaluate LIGHTBLUE on 4 pieces of host code and 3 pieces of firmware. To evaluate the host code debloating, we first keep each of the possible profiles on 4 different platforms and debloat all others. LIGHTBLUE can achieve around 40% code reduction on BlueDroid, and it's 33.7 on Floyd. BlueZ has the lowest code reduction rate, which is 31.7, and BlueKitchen has the highest code reduction rate, which is 49.1%. Besides, we also keep the 5 common profile combinations and debloat all others. Compared with keeping only 1 profile, the code reduction rate drops slightly when keeping a profile combination. To evaluate for the firmware debloating, LIGHTBLUE can remove 65% of the HCI command handlers on the firmware of BCM4339 and can remove 57% of the handlers on the firmware of BCM43430E1. The firmware of the development board, CYW20735B1, has the highest code has the highest HCI command handler reduction rate, which is 83%. Through debloating different profiles, LIGHTBLUE can prevent 20 known vulnerabilities, as the table shows, And out of the 20 vulnerabilities, 15 of them can be triggered over the air. Through debloating the unneeded profiles, LIGHTBLUE can prevent attacks like BlueBorne and BadBluetooth. To sum up, we developed a new technique to identify the unneeded code in the Bluetooth stack, and we built LIGHTBLUE to automatically debloat the unneeded code from both the host code and the firmware. And we evaluate LIGHTBLUE on 4 different platforms, and LIGHTBLUE is open source. That's all for my presentation. Thank you. I'm glad to take questions.